In 1915, Albert Einstein published a remarkable paper with what became the most accurate and complete description of gravity developed to date, the theory of general relativity. Einstein realized that space and time should not be described as independent quantities, but as part of something more fundamental, the very fabric of our universe, space-time. All objects move in space-time, and Einstein realized that gravity could be explained as the distortion of this fabric by the presence of very massive objects. Einstein's field equations relate precisely how the presence of matter distorts space-time. Solving these equations is a challenging task, but even with its complexity, we know that the theory is not perfect. On one hand, it must come to peace with our current quantum mechanical theories that describe the behavior of the universe at very small scales. On the other, if the theory is correct at large scales, there must exist large quantities of matter that we simply cannot see. This last problem is usually called the dark matter problem. But what is dark matter? The idea of non-visible matter permeating our universe can be dated back to the beginning of the 20th century, when scientists such as Lord Kelvin realized that stars near the Sun were moving too fast to be kept gravitationally bound. In the 30s, Fritz Zwicky discovered the same phenomena in clusters of galaxies, and in the 70s, Vera Rubin observed it as well in the motion of stars around the center of those same galaxies. If our theory of gravity is correct, the amount of matter we can see with our telescopes is just not enough to keep such systems from flying apart. With the efforts of astronomers and particle physicists, great constraints in the nature of dark matter have been worked out in the last couple of decades. We know today that dark matter must be made up of some new fundamental particle that interacts very little with all other types of matter we know of. Even with these constraints, we cannot exclude the possibility that our understanding of gravity is just not complete and that we do not fully understand how it behaves at large scales. We must then find new ways of testing general relativity while at the same time understand how it can be used to probe the nature of dark matter. One of the most astounding predictions of general relativity is the existence of black holes. These are regions of space-time where the pull of gravity is so strong that not even light can escape. Black holes interact with their surroundings, making them the stage of some of the most interesting and powerful dynamical processes in the universe. One such process is dubbed superradiance, whereby incident radiation in a rotating black hole gets amplified, slowing the black hole down. Such phenomena is not bound to happen solely with radiation, but is expected to occur as well with dark matter. If this matter does in fact permeate our universe, such interactions might give rise to observable events here on Earth, allowing us both to explore the behavior of black holes as well as the nature of dark matter. Besides black holes, other astrophysical systems such as neutron stars or pairs of black holes orbiting each other might also be the stage for such events. But studying these systems by means of Einstein's equations is so challenging that physicists are usually led to find simpler ways of describing them. As a concrete example, a remarkable connection between general relativity and fluid dynamics allows physicists to understand how dark matter moves in spacetime by studying how waves propagate on the surface of moving fluids. Such analog descriptions of gravity get us closer to understand some of the most exotic and complex phenomena that occur in our universe. What is dark matter? How does it interact with black hole binaries? Can we observe such interactions? These are the type of questions we try to answer at CENTRA, the Center for Astrophysics and Gravitation at Técnico Lisbon, and in the next couple of months, with the supervision of Miguel Zilhão and Vitor Cardoso, I will be trying to answer some of these questions by studying analog models of black hole binaries.